Hi, it's Bruce, and I'm in my Colorado Rocky Mountain lab. And I received an item I purchased recently. It's a General Radio Type 1419M decade capacitor, and it'll give you any capacitance from 0 to 1 microfarad, and it'll do it in 1,000th of a microfarad step over 3 decades. Um, 500 volts peak, and what else? If you're using the two terminals for the reading of the capacitance, you've got 35 microfarads or 35 picofarads of residual zero capacitance. And if you go for a three-terminal arrangement, you cut that down to 16, roughly half. It's in nice shape. It's nice looking. All I did was clean it up with a little bit of Windex and a rag, and it's a nice looking unit in good shape. So I'm happy with that. I did a quick check using this DE DE5000 as my capacitance measurement standard, and I did check my DIR using these. They're actually Soviet made, but they're 0.3% 10,000 nanofarad capacitors. That'd be 0.01 at 0.3%. And it read that dead on. And I'm seeing that on my first 2 decades, I'm in pretty good shape. But on my third decade, I'm as much as 3% out, 3 to 4%. And I tried using other capacitance measurement devices, the BK Precision at Radio Shack. They both read about 4% over on the upper end. So I am pretty well convinced that I've got a problem there, aging capacitor. And it's an interesting capacitance. Now I've taken the thing apart. You take the feet off the bottom, and the unit separates like this, and then you can take these Allen screws, back them off, and that knob will come off. And this is what it looks like on the inside. So you got 3 capacitor banks. Each one consists of a common and then 4 capacitances that they mixed with this unique switching system here. It's a double lug, special made commutator type switching arrangement, and it parallels those capacitances. All right, so what they do, they've got a 0.1, a 0.2 microfarad, another 0.2 microfarad, and then a 0.5 microfarad. And then with this switching arrangement, they take 1 and 2 and make 3, 2 and 2 and make 4. Then 1 and 5 is 6, 2 and 5 is 7, 3 and 5 is 8, 4 and 5 is 9, 4, 1 and 5 is 10. So that's the switching that they do here. And the capacitors are inside these cans. They're potted in. I haven't seen what they look like to tell you, but what I'm going to do, I have to take this whole assembly as a block off. In order to do that, I've got to desolder from this bus line. There's a little clip that attaches to it, and if I can get it desoldered off of there and unscrew that screw there, then I have to desolder that wire from that line, that lug. Anyway, then what should happen is that whole platform should come out. Then I should be able to take the screws out of the end of this tank, capacitor tank. Then I got to decide what I'm going to do. I don't know if I'm going to gut this thing and try and utilize that structure again to hold the new capacitors. What I've done is I've gone through my capacitors in my drawers here, and I found combinations that are going to give me what I need. So like here's a 1, that's a 0.1, excuse me, 0.2, 0.2, and then 0.5 with these combinations. These capacitors are 630 volts, so I should be better than my 500 volt peak that's listed on the faceplate, so we should be in good shape. So that's what I'm doing, and I'll let you take a look as I go along. Okay, well, there's the block that came out. Contains 4 different resistors. And then here are the 4, I said resistors, I meant 4 capacitors. And here are the 4 capacitors here. We have 100 nanofarads, 200 nanofarads, there are 2 100s paralleled, a 200 nanofarad, and then a 500 nanofarad. I padded this one out with 2 10s in series, which added another 5 picofarad, although when I measured it, it was about 3 picofarad. So, that's what the repair looks like. Let's go ahead and run a test on it and see how we did. Okay, we got the General Radio 1419M all set up for a check of capacitance on the upper range. We're going to start out at 0. And at 0 we're getting 28.4 picofarad of residual. And we're told right on the unit here that it's up to 35. So 28.4 is not too bad. Let's mark that down. And go to position 1, which would represent 100 nanofarads. We're getting 100 nanofarads per step, so when I give you the position number, just multiply that by 100 in your head and you know where we're at. So we're getting 99.03 for the first 100. And that's nanofarads. Yeah, went up to 0.04. We'll take it. Go to the 200 position. Starting out at 199.8. I'd be willing to bet if I sit here and watch it, it's going to go up to 0.9. But I think I'll take it. Alright. 300 position. We're getting 299, 298.9. Position 4, and we're getting 399.4. Five, we're getting 495.6. It looks like it went up to 0.7. Position 6, 594.6. Seven. 695.7. Position 8. 794.7. Position 9. 895.3. 0.2, 0.1, in position 10, 994.1. All right. We'll go ahead and run these numbers through the computer and see how we deal. We're running this at 1 kilohertz, which is pretty standard for capacitors. If I had run it at 100 hertz, we'd probably gotten a little higher numbers, and at 10,000 hertz, a little bit lower. But let me run these numbers through. We'll see how we did. Okay, so I ran the numbers, and when I received it, this is kind of what the numbers look like on the top. And you notice that under the error heading, we're running 2 to 3% error, roughly a rough 3%. And then after we did the repair, our indicated error is under 1%, and probably more like an average of about 0.6 maybe, something like that. So we went from 3% to 0.6. When I compare the two together, you can see that we were 2.2, we went down to 0.96, 3.45, 0.1, 3 to 0.3, 3 to 0.2, 2 to 2.5 to 0.8, 2.5 to 0.9. So a significant difference. We improved it a great deal. So it was well worth the doing. And I don't know. I may take another look at the other 2 decades to see if I want to do something similar to them. I may. But there we go. Thanks for watching. Bye.